Okay, I think we are ready to start the morning session. So it's a pleasure to introduce the first speaker, Nigel Mason from Oxford, and we will talk about anti-twistor string theories.
Well, thank you very much to the organisers for inviting me here and for a spectacular dinner last night, and to all of you who have actually made us here after that. So today I want to talk about anti-twistor string theories, and this is built on the CHY formulae, and the work I'm talking about is the result of an occasionally collaborative but occasionally contested work with groups in Oxford and Cambridge. So, what are anti-twistors? So, anti-twistors are spaces complex null geodesics, and they were introduced in the late 70s by Witten and by Arthur Cassidy Green as a vehicle for extended constructions. So Penrose and Ward come up with twistor constructions for self-dual fields, so this which twistor constructions have wonderful properties. They expose the completely integral nature of the self-geometry equations of gravity and Yang-Mills. And there was people wanting to extend those ideas to full solutions to the Einstein equations or the Yang-Mills equations. And for me, this recent work was a throwback to my thesis in the sense that I worked on my thesis on trying to extend the wisdom and green to gravity. But this recent development has stemmed out of, and is actually sort of largely unrelated to what we were doing all those years ago, and has come out of this remarkable formulae that Freddy Cajato, Sonford, and Yuan have developed for tree-level scattering amplitudes based on the so-called scattering equations. And so these are completely explicit closed-form formulae for tree-level SHCs in all dimensions of gravity, Yang-Mills, and that we'll see for many other theories. So, I'll tell you a little bit about those in this talk, and then move on to explain how they arise from the string theories in anti-twistor space. And what I want to focus on in this talk are two more recent papers which extend these models to the new formulae for Einstein, Yang-Mills, Dirac-Kornfeld, and so on the sigma models. CHY have come up with new formulae for these this whole variety of models, and I want to explain how anti-twistors extends those models. But I also want to explain how it is that so these ideas are to a large extent confined to tree-level amplitudes, and what I want to explain is how we can extend these ideas to provide completely analogous formulae for loop integrals on the Riemann sphere using an off-shell version of. So the main message of all of this is that the anti-twistor string provides string theory alpha prime equals 0. So this is so it might be a string, but it's not the conventional string as you know it. It does not have an infinite tower of massive loads. So this is really a tool for understanding conventional theories, space-times, as I said, in ordination. So what's the basic construction? So that a big role is played by a function p on the Riemann sphere. So we're going to be thinking about a scattering process. So you can imagine you've got n particles in that scattering process, and they each have a null momenta ki. So k squared is 0, and the sum of the momenta adds up to 0. And from this we can construct a meromorphic function on the Riemann sphere, which has ki as its pole, as its residue, as n poles in the Riemann sphere. And the scattering equations are obtained by asking that this p is null, So if you compute the residue of p squared at the point sigma I, you find this formula ki of p of sigma I, and this works out to be that expression there, and that is the scattering equation at the point I. And if you think of this as n equations on the n sigma I unknown, then you can persuade yourself that it's quite likely that you're going to be able to solve them. As it turns out, SL2C invariant and 3 of the equations depend on the rest, so you solve n minus 3 of these, and the other 3 are guaranteed. And once you've done that, this is going to be a holomorphic and it's global in the sphere, but in fact, when you think about its Riemann transformation calculus, you find it's really a one form on the Riemann sphere. And one forms on the Riemann sphere, if they're global holomorphic Banach, they have negative weight and to Banach. So the scattering equation is telling you this p squared. You can count the number of solutions, and you get n minus 3 factorial solutions to these equations. So these, I think, were first introduced by David Fairley back in the old days, so to speak. But they were made famous by Gross and Mendel in the context of doing string theory with large alpha prime and very floppy strings. But here, we're going to see that they're playing a role at high tension when alpha prime goes to 0. In fact, it's quick, I think we first observed that these equations underpin the Twister integral formulae for 3-level SMHCs for Yang-Mills. So, okay, so how do you actually get amplitudes out of this? Well, the 3-level massless amplitudes, so these are d-dimensional formulae, so they're KIs for the d-dimensions. And basically, the idea is to impose the scattering equations to these delta functions. So these are double delta functions on the Riemann sphere. And because you've got SL2C, invariance, and so on, you have to do some quotient here. So I'll write my formulas if you're over various expressions involving these delta functions. But of course, what you'll end up with is a sum at each solution. So there are essentially as many integrations as there are delta functions, and so this is actually just an algebraic sum. And so all the formulae have this structure, except we have this IL and this IR, and these IL and IRs will depend on the theory that you want. And there are 2 key examples that I used in the first instance. There's a Pfaffian, so the IL on the polarization data. I don't want this to happen. Okay. I'm going to lose my transparency very shortly. Anyway, okay, so the IL and IR depend on the polarization data for the theory. So spin 1, you just have one of these epsilons, but for spin 2, you'll have an epsilon times an epsilon. And so epsilons are vectors, d-dimensional vectors, which satisfy the usual polarization conditions, k of epsilon is 0 and epsilon is pi mod k. And so one of the ingredients is Pfaffian. So this you write down a 2n by 2n matrix ABC, and the A's are dot products of the K's, B's dot products of the epsilons, and C's are cross terms. And so for Yang-Mills, you get one of the factors is given by this Pfaffian, but the other factor is given by what we often refer to as the Park-Taylor factor, which is a product of the reciprocal of consecutive differences between the sigma i's. For gravity, you have the 2 Pfaffians, you have the 2 lots of polarization. So those are the original CHY formulae. So recently they've found many other candidates for IL and IR, okay, so I'm talking about a car on a photonic string, and so this is really working up highly from zero. So we're going to think of a Riemann surface, which at least for the first half of this talk is going to be a Riemann sphere. And one of the first things you do, when I said what ambidextrous space was, it's a space of complex null physics, and so you have to think of them as living in a complexified space-time. So the space-time coordinates are being complexified to C, and the metric, well, the metric will be flat in this talk, but it's more generally will be a holomorphic function of those variables x. And that the worldsheet model is going to map x and p from the worldsheet into the cotangent bundle of space-time. And here p is a one form of the equations for telling us that p squared should vanish. And so what you do is you put in a constraint. You gauge the constraint p squared equals 0. So E is the Lagrange multiplier which will cause p squared equals 0. But then when you do that, you discover that also is a gauge field, and it generates a gauge field which allows you to translate x along p. So p is a null vector. You can slide up and down this null vector. You can slide x up and down it with this gauge field. So if you think of this as a classical action, this is really telling you that you want your Riemann surface not to be so much in the cotangent bundle, but in the subset where p squared vanishes and quotient it by running up and down p. So this is ambidextrous space, the space of complexified light rays. And this is a space that was much studied in the same way as twistor theory was. So in twistor theory, you think of light rays as being the primary geometric angular. And so here, a point in the, well, this is really ambidextrous space, corresponds to a light ray in space-time. And the ambidextrous space has a whole projective light cone sitting inside it from each point, x in space-time. And those two intersect if x and x prime and are separated. And it's possible to show that space-time geometry is encoded in the just in this complex structure of ambidextrous space. This is proved by Ford in 1983 in a very similar spirit to the nonlinear gravitational construction which was used to understand the Celtial Einstein equation. A big is paid by this potential theta p dx. This is the basic ingredient in the action here. Try to preserve this theta, otherwise you'll get a space-time distortion. Okay. So how do you get amplitudes out of such a thing? You follow the usual string algorithm. So what you're going to do is you're going to you throw in worldsheet gravity, which is telling you how to vary this d-bar operation on the Riemann surface, and you gauge fix, and you get ghosts, and you get ARST, and you introduce vertex operators that correspond to field perturbations, and then you write down amplitudes as some correlation function of those vertex operators. For gravity, we're going to have to add some extra matter fields, which I'll talk about later. So you have to add some worldsheet supersymmetry. I'll leave that out for the moment. And so how do we write down the vertex operator? Well, we're thinking of the vertex operator as being the definition of the action. And the action equals this symplectic potential, p dot d bar x, once you gauge this. And actually that's something that doesn't look like it really encodes geometry, but where ambidextrous, you think p dot dx metric sitting in the definition of that. But according to the Lebrun's theorem, this theta, the complex structure of ambidextrous space determines the original metric, and in fact theta determines because it's actually highly non-degenerate. If you take theta when it's stereoglyphics to the top power, you find that it gives you a whole lot of fun form determines complex structure. So the variation of theta does determine And you could run through the Penrose transform in this case, and you get this formula for the Cartesian variance. And the key point here is that it's this ambiguous representation which is giving you the scattering equations. So this is a delta function supported on k dot p equals 0. So it's the standard momentum eigenstate, and it composes the polarization case, but the key feature is that this also goes with the scattering equation. So this is why, in some sense, ambiguous will give you the CHY formula. And so that's what I want to sort of just briefly explain. So, so the way you actually do the calculation, maybe I shouldn't go into too much detail, is to take all of those exponentials. So we take your product now. These are our vertex operators. You're trying to do a correlation function of a whole bunch of those, and you take them up into the exponential part into the action, because you don't want to take the correlators of exponentials of x and lots of p's. And but if you do that, you still get the equation of x is holomorphic, but now p, d bar of p is going to have a contribution to this term here. And in fact, you get that d bar of p should have a delta function with residue k, the external momenta, at each of the insertion points. And this has a solution p, which is that p we first thought of when we were writing down the CHY formula. And so with this, there's no more correlators to be taken. Everything else is sort of commuting. And so so in fact our formula now reduces to a CHY-like formula, except now with the i's given by this expression here, the product of x and dot p. So we see the basic structure of the CHY formula. We see a formula that they didn't write down. It's a sort of somewhat awkward set of amplitudes, and I think there's a sort of rough guess that these amplitudes, they're done on R cubed, so they correspond to amplitudes that Lance Dixon and Johannes wrote down for gravity with an extra R cubed operator thrown. Anyway, so these aren't so interesting. So how do we get more interesting theories? Well, we throw in some additional world sheet matter. So we're going to decorate an RT with some extra stuff, and these will have an action, SL and SR. So in string theory, of course, you have holomorphic and anti-holomorphic side. Here, they're both going to be holomorphic, but we still distinguish between them, SL and SR. So these are some world sheet matter in formal field theories. And we pick up our VLs from SL and VRs from SR, and we form a total vertex operator, well, with one part from each side. And this will then give us a CHY-like formula where we have their basic structure. Except the IL now is constructed out of SL. It is a correlator of the VLs constructed from SL, and the IR constructed out of the VRs constructed from SR. And the idea here then is this includes situations, Q invariants and discrete symmetries, which are essentially ambiguous analogs of the GSO projections, will rule out any unwanted vertex operators. So, just as they do in conventional string theory. Okay, so what world sheet matter models can you use? So there's a world sheet supersymmetry. You throw in a partner to X, a fermionic partner to X, which is now going to be a spinner on the world sheet. And here you just follow the textbooks, like Polchinski or whatever. We just do what you do in standard string theory. And you have a, but everything here is homomorphic. You have a Riemann string field, which is on the world sheet, and that ages the constraint p dot side to 0. And there are standard vertex operators you write down associated with this, and what you discover is that their correlation function gives you the CHY value. So you have fixed and integrated vertex operators. These are the integrated ones. They correct the epsilon dot p that we had before, but because you've got a couple of fixed ones, you actually put two of these in, and then the rest of these ones, and we get this CHY pattern. There are other things you can do. If you want to maybe couple in a gauge field, or a gauge degrees of freedom, you put three fermions on the world sheet, row A, so these are, you can use these to construct current algebra. There's quadratic expressions in the rows, so these are now 1/4 of the world sheet, and correlation functions of current algebra will give you part Taylor-like terms. But they do have actually quite a big defect. They also give rise to a whole bunch of multi-trace terms, which you don't want at tree level. And one tends to throw them out by hand. These in the original CHY formally, that's what we did. But in the original list of string, these extra terms did have an interpretation. It had an interpretation of coupling the original list of string gravity. And it told you that the theory that you thought you might be dealing with was not necessarily just pure Yang-Mills. And so there's I don't really go through the details of this system. It's what we refer to as a code system. This this has the advantage that it's a way of coupling to a gauge group which doesn't have these multi-trace terms. And in fact, this is crucial when it comes to Einstein-Yang-Mills, because Einstein-Yang-Mills does have multi-trace terms, and you want to look at one. So, roughly speaking here, what we do is we put a current algebra that has level 0, and that's where getting rid of the multi-trace terms, but then the risk is that you actually get nothing at all when you take the correlation function. But what we do is we gauge the spin 3/2 current, and so we end up with a couple of his vertex operators, and they allow you to have. So the structure you end up with in terms of group theory is what is the code. So it's this structure here made out of the structure constants. So usually you get these trace from a product of the algorithms, but here you get these brackets, which you can think of as writing from a diagram here, which has trivalent vertices with the structure constants of each vertex, and it puts together your color structure in this way. And the one at the end are then the fixed vertex operators that sit in the correlator. Okay, so this is all basis for So anyway, this is so I don't want to go into details, but this is a system which has the advantage that it eliminates these unwanted multi-trace terms, and it gives you good control of the bases. So the code system was a sort of introduction, but we can, with these kind of two master systems, with the world sheet supersymmetry and the code system, we can do the three original CHY formally to supergravity, which is has two world sheet supersymmetries, one crest L and one crest R. A hyperotic model which gives you the correct Yang-Mills amplitude but some slightly stiff gravity amplitudes. And if you have two of these code systems, then you get variable scales. And the way that we set things up, all of these models are now critical independent. Before the critical dimensions were maybe 26, well, over there, some of the models. Okay, so how do we get this huge array of models that C, Cacciato, CHY obtained more recently? Well, there are further games you can play with these master models. And, so the first thing you might try to do is to combine them together. And so these are candidates for SL or SR, either the left-handed or the right-handed one. So, for example, you can have two supersymmetries on one side, and what you then find is, so the supersymmetry played an important role for us. It really restricts the vertex operators. You get some extra ingredients in your BRST, And what we discover is that the so what you discover is in fact that if you have both of these, there's no room for a polarization vector. It looks like a Q of variable. You can combine a Walsh supersymmetry with a free fermion on the Walsh sheet S rho, but you can do this in a completely different way from what you did before. When you combine them together, you find you get mixed terms with the spinner of the supersymmetry with the fermion on the Walsh sheet, and that gives you a new type of vertex operator. So that would also play a role. And one of the nice things about the closed system is that because in the closed system we're gauging a spin-free half current here, that plays very nicely with the spin-free half current of Walsh sheet supersymmetry. And rather than gauging them both separately, you can gauge the sum. And this gives rise to vertex operators in which the Yang-Mills vertex before, that these ones and these ones, pick up an extra term in the super. And in particular, they pick up terms which look like fixed vertex operators. And these will then, these will then correlation functions manage to pick up more multi-trace terms. So the point of the closed system was you only get one trace, but because when you mix this in with the Walsh sheet supersymmetry, these terms here can generate more trace sectors. And when we're doing Einstein Yang-Mills, we actually want to have a whole bunch of different trace sectors. So for Einstein Yang-Mills, so for ordinary tree level Yang-Mills, the Yang-Mills fields tree level only have one trace sector, whereas if you're mixing gravity, you can have sort of Yang-Mills doing that, but then you can have your gravity connecting two of these, so you have sort of multi-trace terms. Anyway, so with those, you can choose all of these sort of either the vanilla system or so the vanilla system is S psi or SCS, or any of these mixed systems, and for SL and SR. And we now get a much richer table of theories that we can consider. So we get the original Einstein one with S psi, we get the original Yang-Mills one with S psi, the closed system, but now in between, for example, we get when you have four supersymmetries on the Walsh sheet, you get Galilean theory, completely unexpected things to be able to get directly out of the string theory. Or Born-Infeld, well, that you do expect to get Born-Infeld and Dirac Born-Infeld out of string theories, but really from open strings. These are all closed strings. What's striking also is that Born-Infeld and Dirac Born-Infeld are in some sense non-perturbative things to get out of the string. They're not things you expect to get in a standard perturbative expression. Anyway, so you get all these different theories here, these different choices, Einstein Yang-Mills, Yang-Mills singular, nonlinear signal models, and so on. And one of the striking aspects also is that Galileans have many, many different coupling constants. And so you may ask, well, we're only really getting one theory out of these, and what's characterizing those theories? But it turns out that all of these theories have very, very good soft behaviors. So as the momentum goes to zero, you find that the amplitudes are sort of much less divergent than you would normally expect. And that fixes the coupling constants in these any Galilean theories. In fact, all these theories can be characterized as having sort of better soft behavior than you would expect theories which you generic theories, if you might say, by telling them. Okay, so that was covering the different theories that we had. What I want to do now is to how we can extend these ideas to higher loops. And in fact, in some sense, I mean, there's a well-trodden path there already from conventional string theory. If you want to do a one-loop formula, you assume that your world sheet is an elliptic curve or a torus, and you calculate your string partition on torus or higher tenors for higher loops. So this is something that the Cambridge group did back in 2013. Can you set up the scattering equations on an elliptic curve? And so you take the representation of elliptic curve as complex k divided by a lattice, and you have a modular parameter tau, or its exponential, these are the two. And again, the ambiguous string will tell you to solve the equation d bar of p is given by. And so what you have to do is you have to write down a solution for p which has a simple pole at each of these zi's with residue by the ki. So if you're good with piece functions, this is actually an easy thing to do. So these are the standard piece functions. And so this term will give you a simple pole. And what you find is that there's a zero mode. And so dz is something you can always add on. And another momentum vector. And we will think of this as a loop momentum. This is going to be actually identified directly with the loop momentum. I've added on all these extra terms here. So this wasn't actually done in the original paper, but if you follow the standard string theory routine, you get something non-polymorphic right on here to make it modular invariant. But that means you end up with non-polymorphic scattering equations. Everything here has to be polymorphic. So you can't do that. And in fact, Sally talking showed that it didn't factorize properly if you had non-polymorphic terms. They had something which wasn't modular invariant, and it's only modular invariant when you integrate out loop limit. Anyway, so we're going to do the same thing. We're going to try and set the residues of p squared to 0. But of course, now on the elliptic curve, it appears in one form, local one form on the elliptic curve, and so p squared is now going to be some constant once you've killed all the residues of p squared. And so you have to somehow arbitrarily just set p squared to vanish at some point. I mean, it's a constant, so it doesn't matter which point. The other thing is that you have a translation freedom on the elliptic curve. It's no longer SL2C, just a translation. So you set one by hand, and then imposing these scattering equations of 2 to n will imply the scattering equation at Z1. So you'll still get the polymorphy. And but then we, as I said, we need to impose this extra p squared equals 0 at some point. So we're going to have some integrand, which will be some worldsheet correlator here, right, Q. And the other feature here is that we have to integrate over the modular parameter as well, t tau. So this is, unlike the ordinary string theory expression, in string theory you have d tau bar over the imaginary part of tau to some power. To some power. And here everything has to be polymorphic. And so in the Sardi-Torquin analysis, they also made a projection here that if IQ is just equal to 1, this should give you a permutation sum of n-gons, and they justify that by looking at factorization properties. But we're going to use a different device to analyze this. So part of the point here then is if you just go back to this p squared equals 0 scattering equation, by the time that you've imposed all these other ones, this is just really an equation on tau. And so in the tau plane, we've just got a bunch of points, bunch of values for tau, which are going to contribute to the integral, which are contour integral. So all of these things here, you can think of as being residues of 1 over p squared, all of these points here, of p squared equals 0. And, but d tau is really dq over q. This has a simple pole of q equals 0, which is really imaginary part of tau. And so we can do an integration by parts, or an integral formula, to turn this into something at q equals 0. So as you go up the modular plane here, your torus here starts pinching. It gets longer and longer, or if you do a form rescaling, it gets thinner and thinner at some point there. And eventually, it degenerates into something with a torus with a sphere with double points. So you think that's a green sphere reaching around and touching itself at that point. And this 1 over p squared then degenerates into 1 over l squared. So under this sort of contour integral then, we get a formula that's now on the Riemann sphere, but at q equals 0. And there was a great puzzle before, you see, as to how it's this sort of formula like this with all these theta functions could give you something that's essentially meant to be a rational function, because it's got to look like a standard movement parameter. So here now, it's reasonably clear that it's just as likely to see the rational function as the original CXY movement. So q equals 0, pz degenerates into giving you this formula, which is an extension of the standard trio version by this LD sigma and sigma. This is something with a pole at 0 and infinity, so this is really dz on the Riemann sphere, so you think of it as a global polymorphic form on the nodal curve. And the scattering equations here then are just telling you that if you take p squared minus l squared times the global form, you get some. So the off-shell scattering equations now are the condition that the residue of sigma I of s should vanish. So anyway, so we now have a formulation on the Riemann sphere, and we now want to actually know that it's true. But we're getting everything in a slightly sort of funny form. We certainly have with the initial formula we had, we set the prefactor equals 1. This is really an end-on. You can see how does one actually see what you get from this? Well, at 4 points, you can solve the scattering equations and just work out what you get. There's only 2 solutions at 4 points. And you get something which you can sort of see how to understand as arbitrary many points. You get something, so you get this formula here. So this is 1 over L squared we had up there. And then we get the linear factors in L, just a product of reciprocals of linear factors in L. And so this is something that we can see is actually equal to a standard end-on, but only after doing some partial fractions work and shifting the L on different terms. Okay, once you've done this, we have to think about what these integrands are doing at q equals 0. So you look at the limit as these i's at q equals 0, and so we get brackets as before, but the string theory integrand was a sum over spin structures and stuff, so we actually get sort of a number of contributions here. I've actually missed out the odd spin structure of this expression here because you can ignore it as convention is less than 9 for one loop. And we get this formula for the one loop supergraphing integrand. So again, we can check this algebraically at 4 points, and at 5 points it checks numerically. So this is now going on. But you see, we have no expectation of getting Yang-Mills right at one loop. But you can still just write down the formula. What you do is you replace one of the Clapeyans by a par-Taylor factor, but you make sure it runs through the loop, 0 infinity. And you just sum over all possible ways of doing that. And again, this checks algebraically at 4 points and numerically at 5 points. And you can also do the same for the biagonal and scalar, so which is a non-supersymmetric theory. So in all loops, you can imagine doing the same thing. You can imagine doing a contraction of your Riemann surface to lots of to a nodal Riemann sphere, by contracting G A cycles, and your P then will have the standard tree-level form plus these omegas, and the omegas essentially have a pole at each end of the mode. And we can write down off-shell scattering equations where P squared minus that lot vanishes, and we can write down formally. And you can see that you can again write down conjectures for all of these theories of arbitrary group order. Okay, so just to summarize then, we've got a parallel alpha prime ambiguous string, which gives rise to gravity, Yang-Mills, and many other theories, incorporates telekinetic duality, extends, and although critical models, only critical models will extend to loops on a ring surface, you can imagine many of these models will extend to loops around on a ring sphere. And just one last small point is that one of the things that's controversial in working with loop integration, you actually have a canonical choice of loop momentum. This story seems to pick one out for us, and that's something that we've been struggling with in gravity theory. So loop integration is plainly angles, but this is a non-planar story. So thank you very much.
Thank you very much. And any questions?
Yeah, you ended up with this.
What's peculiar here is that go back to this formula here. This is, of course, one of the first things you come to, because out sleeve, so to speak, and prove in the first commas that an equalization of gravity is finite, or not. And but what you find here is actually this is a suboptimal form for the UV finite. So for the, you see this is meant to be the n bond, so you'd expect this L to the 2n. And we have one, so we do have n denominator factors, but L squared is only, you don't have L squared in one of them, you have one called linear. Now, in fact, you can check the U, but it's more of a factorization argument. And so it's something that you can do, but it doesn't come directly out of the formulae on the modes. It's something which will come from some analysis. So I'm hoping eventually we'll be able to do some checks, but it's not yet at this stage.
Okay.
I have a question on the off-shell. You expect to reproduce something like where the error recursion relation for currents?
Well, there's only, you see, one of the things that makes this work is that they come in pairs. So you can see here that getting an L and minus L there. And I think the very speed of currents, you would have to have just one off-shell. But this is what we do.
More questions? Comments? Okay, if not, let's thank the speaker once more.
Sorry.
This announcement.
Yes. If you need your boarding pass printed, please email them to IGST, whatever, at .org. And before the end of the lunch break, then I will print them out. If you need a certificate of participation in the conference, please also email us, and we will print one out. And there will be an extra coffee at the end of the day. So there's going to be an extra coffee, I think, after the last session, and then We come back at 20 past.
Back to the Berlin future. Wrong on so many levels.
What did you say?
Back to the Berlin future? No. I'm sorry. Where's your t-shirt with that?
Patterns? Yes. Those kids t-shirts that have everything, you know, the Acropolis
Yes.
and then these guards that have the skirt, everything all together, all different periods of Greek history.
Because they have this decoration that's used by all.
Ah, the meander. Yeah, meander, yeah, has now gotten a better reputation. Well,
No.
they use the meander, but if you turn it around, it's almost like a swastika.
Yeah, that's why they use
Yes,
it.
exactly. You just need to look at it the right angle and understand.
I saw a video of one of the leaders that said, we may read with our hand extended, but we have our hands clean.
Exactly.
That's not how we want to end this sentence.
Well, the thing is, the way Syriza accepted this agreement, they became a pro-memorandum party, pro-austerity party. Basically, they left the ground free for the common law, and they gave speeches, there was a discussion about the new law that will accept the agreement and so on. And they used it extremely well. They said, exactly mistake, now Syriza has to.
20
Okay, I think we are ready to continue. So the best option to use here is Salini from here. So about the station operator and also the attitude.
Thank you very much. It's a great pleasure to be here at this conference. I'm going to talk about some work done with Andy Cooper, Paul Hestorp, Brenda Benante, and Laura Maniani. There will be two parts to my talk. In the first part, I will discuss some calculation of the volume dilatation operator using some commercial techniques, and in particular, commercial techniques applied to the calculation of two functions. The first attempt to discuss the calculation of down on application of energy dynamics to correlation functions, and then on generalization reality. And this usually end up being quite simple problems in single scale. So the resulting integrals are quite simple to raise some advantage in pursuing some techniques. And the second part is slightly disconnected. So I guess everyone believes that there is a single Yang symmetry between energy forces and this, but it's got some slightly different manifestations, say on amplitudes and on the dilatation operator. So we asked the question whether we could connect these two actions, and more precisely, derive the action of the Yang on the dilatation operator from the non-Yang symmetry of the scattering values. So this will be the second part. So let's begin with the first part. Well, now everybody knows there's been some quite enormous progress in the calculation of scattering amplitudes. Last week there was an interesting conference in Zurich and which discussed this progress. And one of the long-term goals that we decided for ourselves at Primary was to try to extend some of this progress to quantities which are less on-shell. And the first thing you can think about, which was discussed many times in this conference already, are form factors. So what you do, you take some interesting operator to your theory, you apply it to the vacuum, and then you project onto a state. And then you take Fourier transform, and by translational invariance, it turns out the only thing you need to compute is the operator at zero, and in this particular matrix. So these are form factors, and they appear in a very large number of interesting physical contexts in particle physics. Scattering, classifying to hadrons. What I would like to mention, which for us was quite an accidental finding, is a connection between something you may think is quite arcane or disconnected object from phenomenology. So the form factor of having those operators in any force with Yang, and there's a very quite stunning connection with Higgs amplitudes in QCD, and QCD and QCD, whereby the maximum inference and delta part, so the most complicated part of this scattering amplitude, is computed precisely by the electron force. This is still something unexplained, as I mentioned, just because I think it's an interesting point to connect supersymmetric theories to really physical theories. And of course, the next step is to, in this path, is to try to apply on-shell techniques and all the advances which have been made in amplitudes to correlation functions. And the simplest correlation function is the two-point function, and that's got to do with the dilatation operator. So that's the connection that I would like to outline. I just added some last-minute slide following Peter's speech yesterday. We mentioned the G minus 2 of the electron, and the G minus 2 is a form factor. It's a form factor of the electromagnetic current. And in fact, we got interested in form factors precisely because of the G minus 2. So I thought it was interesting to mention it. Now, the G minus 2 is a number, of course. Say, what do you see simplicity? Well, simplicity comes from if you look at higher group corrections, it's quite interesting or curious that these are equal more or less to 1, despite the fact that you sum many diagrams. So this was designed that there should be wide oscillation between different final diagrams, even in this off-shell, slightly off-shell quantity, which cancel, and at the end you get a result of the total one. So this is a clear example of unexpected simplicity in this slightly off-shell quantity. This is 3. And it was completely
Do you remember what the number is going to be?
no, but it's more or less the same. I don't know the slide that comes in a moment. Because all of this came from something we came across, was teached by Frederick Sitanovich, who when he got some prize in Denmark. And so the story, I mean, I won't read this, but the story was that he was invited to Caltech by Feynman to give a talk on this results, this integrals that he had been computing with Sitanovich. And they started panicking because his number was equal to 1, not equal to the number of diagrams, so he understood that there was something quite special about this quantity. And then he went on to conjecture something quite remarkable, that for each order somehow in the perturbation theory there is some kind of constant number which might appear. So he went on to even to suggest that in some cases the perturbative series could be exact. So I did this for you, we also do it then in the slides, and let's go back to the operator.
That cannot be.
You thought this better.
No, because it's classical.
Yeah, you should read these things. It's extremely interesting and it suggests a lot of things that you disagree with, that everybody disagree on. It's an interesting read. But it's a fact that we show that perturbation theory. Anyway, this was a motivation for us to start studying with from others. So I want to say. Now let's go back to the dilatation of Pareto. Now there are two classic ways to compute it. One is to compute the renormalization of this particular L plus 1 function with one composite operator and many elementary fields. Now an interesting approach which has been followed by Nicola Humboldt is to further go on sharing these fields and this transform this object into a form factor by doing process one introduces infrared divergences which are however under control, so one can subtract them and be left only with connected to the dilatation operator. So that's one very interesting approach. Another approach is that of renormalizing directly two-point functions, so that's what we are going to follow. So in this case there are only unique divergences and there will be single scale propagated integrals because dependent on x12 squared will be also accompanied by the capital, which is a sign of divergences. And in momentum space they will end up being two integrals at n loops. But these are single scale integrals, so they are quite well, are two loops which means four loops, so they are completely there's a basis and so one can be discussed about this problem. Now a very quick review of what we're going to do. So we are looking at two-point functions which on the basis of conformal symmetry have this structure. Gamma is the Ramos dimension, which is what we want to obtain. By expanding this in G, we see that gamma precisely multiplies the logarithmic divergence. So what we want to do is to look at these UV logarithmic divergences which correspond to poles in modular epsilon in dimensional regularization. This was quite schematic, but one can define precisely the dilatation operator and then expand into perturbation theory. And again, if you do this in dimensional regularization, you see that what you're interested in is the extraction of the 1 over epsilon pole in dimensional regularization. And then that's what we're going to do next time. Now let's start with the simplest possible case. So now we want to test some new methods. We look at old results, which we try to rederive with new methods. The first you will think about is the SOC sector, which was discussed and connected with durability in a Hansen paper. And the sector is closer to a loop, so it's very useful to study the sector. And if you look at the Taylor limit, again, at one loop, only nearest neighbors will interact. So we only need to discuss this max loop. So we are going to discuss the ABCD about asymmetry in this. Now, just based on asymmetry considerations, this two-point function has a structure. So you can see the three different asymmetry structures which can appear. One is called the Frey space, permutation with identity. And so there are three numbers we have to compute. So we have to compute these numbers A, B, and C, which were found by Nazareno and included by these expressions. And of course, these three numbers precisely end up in this very nice Hamiltonian, which is an integral function. So now we want to derive these three numbers. And we're going to do it using on-shell or on-shell inspired techniques. Now, just before we do that, I want to just remind you very briefly how U-V divergences arise. The prototypical U-V divergence arises from this four-point vertex structure. So you have two propagators connected from x to x1 and two other propagators connected from x to x2. They give rise to this U-V divergent integral, which is precisely about the divergence as advertised before. Now, usually these calculations are done in position space. But now we want to apply on-shell techniques, so we have to see how these things looks like in momentum space. And just a very short algebra will show that you obtain this expression, and this is nothing but, so this is a double integral. Each of these two red integrals is a bubble, which is further Fourier transform. So now let's see the Fourier transform of this object. And the Fourier transform of this double bubble is given by two free propagators times 1 over absolute divergence. And this 1 over 8 squared will end up in the definition of the top bubble. And if you compare to trilateral is just a single bubble which gives two propagators. So here we have two propagators, but they are also addressed by this U-V divergence. Now this was just a 4-point vertex, that's not what we are interested in, but it's what we are going to address with something else, and that's why I show it now. Okay, so let's see the first, well, even historical, the first novel on-shell technique which was discovered, is MHD diagrams. Now, MHD diagrams is a new perturbative expansion of Yang-Mills theory. And this was found by Shadow Sarcher and Witt a long time ago. And the main idea here is that there are certain new vertices which resum many final diagrams. And these vertices are given by a particular off-shell continuation of the MHD amplitudes. The MHD amplitudes, they have a lot of fascination because they are very compact, and they already resum very large number of diagrams. So now they are elevated to the new fundamental vertices of the theory. Of course, there's one issue, all these spin of brackets assume that the legs are on shell, and now we want to use this as a vertex, so we need some off-shell continuation, and the off-shell continuation which is correct, which works, is precisely what I wrote here. So what you do, so you want to find a spin that you can plug into these expressions. So you take the off-shell momentum of some internal leg, L, multiplied by reference spin psi alpha d. And you might recognize that this is very similar to what people do in light quantization of Yang-Mills, and there is a very nice connection. Namely, one can derive MHD rules by first going to the Latin gauge and then performing a certain change of variables in the path integral, which is Jacobian integral. And the MHD diagrams were tested as well. They work at 3 level, were also tested at 1 loop, and also work for the constructible part of amplitudes, even in non-supersymmetric theories. One thing I want to mention is that, which will be relevant later, is that there is only one spin-off with a negative chirality psi alpha. There is no spin-off psi alpha introduced. This could have some relevance later. So, and this is related to the fact that the MHD amplitude is holomorphic. There's only one kind of spin, which is rather unusual for an amplitude, but it's not precisely for this MHD amplitude. Now, why is this useful? It's useful because there's a single MHD diagram that has to be considered. So again, we want to look at this 2-to-2 process, and we want to find these three numbers which correspond to trace, permutation, and identity structure. And there's just one diagram. So here there are 4 scalars. We want an MHD amplitude. So at 4 point is just this vertex to consider, and it's attached to 4 scalar fields. So what we do, we throw in some indices such that we get only one vanishing structure at a time. And for example, you can pick these choices, and there are 3 scattering amplitudes, which will be then continued off shell vertices. But one is very simple, it's equal to -1. So that means that we just have, so we have 4 propagators times -1. But this is exactly the vertex I showed before, so we already know the result that is going to be equal to -1, which is the right result. So now the problem is, of course, find the other two coefficients. In the other two cases, we have to address this double-bubble structure given by the four propagators, these two new terms, this amplitude and this area. So let me show you briefly how you do that. I want to stress that the idea here is not to compute exactly this object, it's only to pick divergences. So the name of the game is to try to compute as little as possible, just to get the divergence. So in this case, this double-bubble integral that appeared before is stressed by the presence of this MHD amplitude. In one case, as I said, there's nothing to do. Let's look at the next case for the identity structure. We can just rewrite this amplitude in the following way using one of the famous identities, as Cousin identity. And well, at this point, you have to use the offset continuation, so you have to think about the integrals. So well, we use this CSW that shows the sufficient with an offset continuation, and which transforms this red term into this yellow term. And then we just use momentum conservation, this L1, L2, L3, L4, the four momenta, and instantaneously you transform this into this expression. Now you don't need to do anything. So the first term corresponds to this double bubble. That's a logarithmically divergent integral. So that's a boundary of being convergent. So any extra power of momentum or loop momentum in the denominator will make this finite and can drop it. And you can see here, so L is the Fourier transform gradually, but the L1 and the 3 they count. So you have L1 and 3, and here you only have L1 and 3. So this is manifestly finite, and you just drop it. So what is left is well, this 3 and -1 and this 1. These are two of the coefficients we wanted to get. So there's just one more coefficient to get. Now I won't bother you with details. There is a new MHD vertex to use. And then what you do, I won't describe this in detail. You just use momentum conservation to divide this into the sum of 3 terms. And now these 3 terms have instantaneous interpolation in terms of linear bubble integrals, the first two at least. And the last one needs some more rewriting. Again, you don't need to follow this. The point I want to make is that 2 terms can be dropped, one survives. So let me just focus just for a few more seconds on the term which survives. So all of this red amplitude becomes, by just doing trivial algebraic manipulation, becomes this single term over here, and then two other pieces which survive. So this is the term which survives. So if you integrate in L3, so this is a linear double bubble. There's only one insertion of L3, and the only momentum in the game is L, so this L3 is going to become equal to L times some coefficient coming from a trivial integral. And you see, for example, the first term will become L1 times L, and this will be completely identical to the denominator, and the denominator will cancel out. But that's something good because remember psi is this reference spin which is supposed to go out the offset continuation, but then should disappear. This is not, it's been proved, that's also to see it explicitly. And the second term just vanishes. So if you collect all these results together, you get this other coefficient equal to 1/2, and you get agreement with this in another way. So it's the message is it's a nice and simple way to compute the dilatation operator in this sector upon loop. Some comments. I just mentioned the excited dependence. As I said, it's guaranteed to drop out. It's been proved by Cacciato, Sergio, and Witten. It's known because CSW rules or HG rules are connected to the Lycon quantization of the H theory, so we know that the H dependence disappears, but still it's nice to see it explicitly. One way to see it is that there is absolutely no way to get a Lorentz invariant quantity which involves this P naught psi in the game. The only quantity you can think about is this, and that's zero because this object is a unit matrix that goes out, and then psi is equal to 0. And the important point, which connects to what I said before, is that the other quantity you could have thought L dot psi, but we cannot form it because we only introduced psi alpha, and we did not introduce psi alpha dot. So this quantity cannot appear. For people who are interested in energy diagrams, you may wonder about self-energies, and we found a long time ago that there are no self-energies to consider in this case. And I'd like to connect to some interesting, nice work of the Berlin group, which so they performed exactly the same before ours, based based, however, on energy rules in crystal space. And they want us to face certain interesting integrals, which are divergent and need some line splitting regularization, which in space-time will correspond to some point splitting regularization. And it's quite remarkable they managed to do the integrals and to regularize them and to perform them. And we were discussing this with people at the Ambiguous conference last week, and it would be quite interesting to connect more precisely the technical details of these two calculations, and in particular these integrals, to map these integrals to the energy diagram integrals in position space. End of energy diagram. So let's now revisit the same calculation with another. So again, following history after energy diagrams, and generalized unitarity again. So now we want to compute this correlation function, this two-point correlation function, using cuts. In particular, by trying to cut as many legs as possible. And I should mention there are early applications of these method correlation functions from Engelund and Boylan. So now the ingredients here, there will only be amplitudes and cut aggregates. No offset continuation. So let's quickly revisit the case of the identity contribution. So there was the permutation was trivial, so the only terms left were identity and trace. So there was this second term which before I showed can be dropped out because it gives rise to a finite integral. Finite integral, you can immediately write it down. It's simpler to write it down in this context than in the energy case. And it turns out to be shaped integral, which in 4 dimensions is finite. And therefore we can call it. And okay, I won't bore you with details. We can do exactly the same thing with the other trace structure, and we find this one-half coefficient by just evaluating very clear integrals. An extension of this, so this was the SO6 sector, then we tried to extend this to another very simple and very interesting sector, namely the SU2/3 sector. It's another closed sector which also involves fermions, so it's interesting to see what happens when you have different particles. And there's a set of letters which is very limited. There are only these 2 fermions and these 3 scales. And the Hamiltonian was known from a very long time. It's given by this symbolic structure. So A are the R-symmetry indices in this subset, and alpha fermion indices, the spin indices. And again, you only have to look at very simple subclass of diagrams because they are only nearest neighbor interactions. And in this case, you can see by just staring at this expression that only have the identity and permutation structure and the trace structure. And as I said, this is interesting to look at because there are new interactions, new amplitudes that you have to look at. So just let me highlight some of the salient features of this calculation. The first salient feature is that you have to attach this amplitude to the operator by using 4 factors. This just comes from unitarity. So, for example, you can have here a 4 factor which involves a scalar and a fermion. So that's used to connect the amplitude to the operator at this point, this point, this point, this point. And there will be new amplitudes you have to consider involving 2 fermions and 2 scalars or 4 fermions. And there will be new reductions of integrals. They are all very simple and can all be done on a piece of paper very easily. And new trilateral structure to consider. And if you go in the end, you will produce very nicely this result of bicycle more chemical. Now again, another thing I want to mention, which is in progress about so 2 calculation. So we decided that we want to apply these techniques to higher loops where more interesting features and unitarity also becomes more challenging. So we decided to look at the SO6 sector, which is not closed, but the Hamiltonian is known by the work of geometry and Plevka. And just let me just show you something simpler. So as I warm up the SU2 sector, which is closed and simple to describe. In this case, there are only these letters, and this is the structure of the Hamiltonian. So again, there are 3 coefficients to find, which were found to be equal to these 3 numbers, 3 very simple numbers. And you can see in this case, well, this is called no shuffle. Here is one shuffling of the fields or asymmetry indices, and here is the maximal possible shuffling. And if you want, these are the three instructions from the activities. So we are after these three numbers. So let me just quickly show how you can compute them. The strategy again is to compute now two lookouts of this correlation function. And this is quite new, but first it's new because the dilatation operator at two loops is not immediately directed to loop renormalization constant, because we have to subtract from this. And also, most importantly, it's different because we have to compute these three degree processes, which amount to considering 6 point scattering amplitudes in this particular two-party 6 text. So let me just give you some very simple examples because the calculation of details are quite complicated. So the simplest case we describe is the maximal shuffling case. And it's simple because the relevant amplitude which will appear here, which is shown here, so these are the 3 cut legs on 1, 3, 4, 5, 1, 2, 3, up to 6 are the cut legs. So this one is very simple. And simple means there is no numerator. Now the presence of numerators carries a lot of ambiguities when you do linearity. Let me just give you an example. Imagine you find a numerator which is of the kind L1.L2, where these are loop legs, and they're cut. So L1 squared, L2 squared are 0. But then you have an ambiguity whether you can rewrite this in this way, L1 plus L2 squared, or you just leave it like that. The difference, of course, is these two cut propagators which you cannot see. So what you have to do, and this is just it's done, it's doable, it's just more complicated. You have to investigate other cuts where these particular momenta are not cut to probe whether this particular numerator has to be written in this way or you have to leave that for any intermediate possibility. But it's good. This is some people that have highly efficient technologies for this. But in this case, we don't have to bother because the numerator is 1, so it's quite easy to describe. And in this case, you just get this particularly simple integral. As promised, it's a one-scale for-loop integral. And there is a known basis, so we just prove it up and this particular result. And then you have to form this combination Z2 minus 1/2 Z1 squared. If you do it, you quickly arrive at this result. Okay? Just perhaps I should stress you embark this calculation because you know that there is a known basis of for-loop integrals. Otherwise, you may think twice. Another example, I shouldn't spend much time on this. So this is a more complicated case. So for example, we can look at the half BDS operator, which of course should have 0 numbers dimension, and this implies a relation between these three coefficients. So this we know, but nevertheless you may want to go and check this from amplitudes. But in this case you face this particular scattering amplitude in the cut, and now you see that there is a number of ambiguities in the numerator. So these three terms end up in these three integrals. Again, they are all known, but we have to discuss these ambiguities. So this you do by inspecting different cuts, and then you find what is the correct answer. And it turns out that you have to complete the propagators, and this leads to a result which is finite, and therefore we drop it because there are no linear versions. I also want to work mention a nice alternative approach, which has already been tested in the SU2 set of IGST group, another group, where they computed the two loop from Papa, and they, in particular, they were able to disentangle the UV divergences from the infrared ones, and from this you can extract immediately the dilatation operator, and they also were able to compute what we call finite remainder functions, which structure and I won't have time to discuss the result, but I find it very. Okay, let me now move to the second part of the talk. So as I said, we all believe that Canadian symmetry is a fundamental property of any closed William and you may find some of you, we found curious that it manifests itself in a slightly different way in the realm of amplitudes and in that of the dilatation operator. So what I'm going to show you now is a derivation of the action of the Canadian on the dilatation operator, starting from the non-action on the scattering amplitudes. Now, so let me remind you two facts, so let me just remind the action of the Young, first on amplitude and then on the dilatation operator. And the statement number one is that the three-level S matrix of n equals 4 so Young is Youngian, well, covariant, or if you just redefine slightly operators, is invariant. Well, among the generators, of course, there are level 0 generators, which correspond to the ordinary superconformal group, which, well, I think they are, that's very well known. But then one can form this bilocal level 1 combination, which corresponds to the level 1 generators. And the interesting results of this paper is that these level 1 generators were connected to the dual superconformal group, which had been discovered just a bit before. So in particular, let me give two examples which will be relevant in the following. The level 1 generator associated to momentum corresponds to dual conformal K, and the level 1 generator associated to Q, so the symmetry is just the dual superconformal generator S. They already appeared all in the talk by Niklas 2 days ago, and there will be also interesting connections to restore in a couple of slides. Now, the important statement is that amplitudes are covariant, or if you wish invariant, under the dual superconformal group. So, and this gives rise to this kind of invariance. Now, that's statement number one. So the S matrix of n equals 4 three-level is invariant. Now, let's look at the dilatation operator. Now, here the statement is slightly different, only slightly different. So the dilatation, the complete dilatation operator is only valid up to certain boundary terms. Here L is the length of the chain. And Donald and Witten, they found this statement, and they were also able to show that this statement is equivalent to a statement on the two particle densities of the dilatation operator. So again, what we really want to prove is this second equality, where the level 1 generator Q, so Q is the level 1 generator, acts on the Hamiltonian density which acts on sides 1 and 2. By this expression found by Niklas and Michael. So what we want to do, we want to prove this relation using non-flat matrices. Before doing that, I want to just make two comments. The first one is that the proof of Donald and Witten is based on acting on irreducible representation of PSO2 Of course, you can expand everything you want with this representation, so it's not important, but it's quite peculiar that it's really crucial that you have these representations in order to find this relation. Maybe it's just a feeling, it's not in concrete, but you may notice that. Now, the other thing you may notice is that the left-hand side of this equation is certainly a one-loop quantity because there is a one-loop dilatation operator. But the right-hand side, well, there's nothing really looking like one loop. This acts on a state, and here there's another state, but there's nothing of a one-loop character. And this is quite interesting. It might be reminiscent of things which happens in amplitudes. For example, the fact that infrared divergences are always proportional to the three-level amplitude, where somehow you lose the loop character of the expression. Of course, here is actually square, so this is one-loop quantity. There's nothing wrong going on there, but you may wonder about this. And in the Donald proof, this is achieved by this rather remarkable identity. You make up this particular combination, which is equal to 1, and this rise to this overall coefficient there. So basically, we want to have a feeling on how this would happen by using amplitudes. So we want to divide factor from factor. And the main tool is a very intriguing formula which was found by Siebel a number of years ago, following some inspiration by Niklas Weissert. I'm going to show it quickly in a moment, but let me just mention what are the building blocks of this formula. So they are the 4-point three-level scattering amplitudes in n equals 4 Julian case. This must have something to do with the process because it's something to do with the process. And then three-level minimal form factors. So form factors made of the letters which will be relevant for the dilatation operator. And I'm going to spend some time on this slides. And these form factors will represent the states in which the dilatation. So the idea is to use the action of the Young generators on the amplitude of this remarkable formula to derive the action on the dilatation operator. of this, what we're going to do. So again, we will consider the same signal trace operators, but now there is no restriction on the letters we can consider. And now we want to connect this to scattering amplitudes to the spin-on-IGST formalism. So one way is to pass to the oscillator representation of the states. So it is well known that these letters can be represented in terms of oscillators. So two pairs of bosonic oscillators and one pair of fermionic oscillators. And this them up to the state that everyone knows very well. Now the connection to the spin-on-IGST formalism is that you can represent these commutation relations by using spinos and spinor derivatives. For example, lambda commuted with d by lambda is 1 and is represented this one here. So in fact we can go straight from the letters directly to the spinos. We don't really need to pass through the oscillators. And then in N4 it's completely natural to combine the spinos and also the Grassmann variables which are needed to and scalars and negative gluons into this object capital lambda. Now in this language, so that's the point, a state is just a polynomial in these lambdas for each particle, for each side of the chain, but you have to make sure that you satisfy some physical state requirements, which is the value of the state. Just two examples, so if you want to look at the half BPS operator, for example, 512, 512, that's represented by this combination of eta variables. So the top index is the asymmetry index, so 1, 2, 1, 2. And the bottom, the downstairs index is just the position of the field. And similarly for other operators. Now the very nice P.S. dilemma was that this quantity P, which in the Spiller paper was never named, is actually just a 3-level minima compactor of the corresponding operator. So you take an operator, the operator you're interested in, and you consider the first non-vanishing compactor, which has exactly the same things as an external state. And that's exactly what you get. It's one mapping. So again, for example, if you take something which contains this particular, let's say, letters or Grassmann variables, that corresponds to the form factor of this operator with the same state. That's what we call minimum form factor. Now finally, I can show you this. This triple formula. It's a phase-based integral. So this measure d lambda 3, d lambda 4 is a phase-based measure. So it's an on-shell measure. So everything which enters this formula will be on-shell. That's the connection to amplitudes and to factors. The measure can be written this way, for example, and then we have to model out the integral transformations. It's kind of convenient to read it in this form for technical reasons. Now, as advertised before, A1, 2, 3, 4 is the super amplitude at 4 points, and then you go for super units, and P1, 2, or here P1, 2, P4, or 3, they represent the state on which the dilatation operator acts. And this phase-based integral, there are two cut particles, so this is a two-particle cut. Now let me show this nice interpretation in terms of form factors. So let's look at the first term, for example. So I drew the diagram in the opposite direction. So here is the amplitude, the fact is here, and these two legs are cut and integrated over with the appropriate phase measure. There is also a second term, which corresponds to the second term in this Spiller formula, and this corresponds precisely to eliminating the infrared divergences which are present in this integral. So this integral is divergent both in the UV and in the area, and the second term in the Spiller formula, which was added quite by hand by Spiller in his original paper, precisely cancels the IR divergences. And the IR divergences, you see, this is the unmodified 3-level form factor. This is because this divergence is at the exponential. So that's the only thing you can have. That's why this P1, 2, which can go outside the form factor. So whatever is left over is the discontinuity of the UV divergent integral, and for now there is only bubble integrals. And the other thing to say is that bubble integrals are, their discontinuity is finite. And that means you can compute this formula exactly in 4 dimensions, forgetting about any regularization. That's another interesting advantage of this formula. Very nice feature of this formula. So this is phase space integral in 4 dimensions. The connection to the dilatation operator comes from as field by integrating out the momentum delta functions, and one obtains this. So you have only 2 integrations, which is what we expect to get. And you get this quite nice formula, where this 1 and 2 represent certain rotated spinors according to this matrix. It's a very practical formula. It's one that you can code. And also, it was shown that this reproduces very quickly one of the forms of the dilatation operator, namely the form found by Dyson. So we have 2 forms basically. We have one, which we started with, the then you eliminate momentum conservation, you get this unintegrated formula. It's very nice, but it's very non-obvious how to see how this relation could be realized on this formula. So what we want to do, we want to add with Q on the first formula, on the unintegrated one. Because there are attributes, and basically we want to use that the action of Q onto the amplitude will be 0. We know a lot about that. So that's what we want to do, and how we do it. It's very simple to do, so I don't need much time. So, and I will show you, of course, the simplest example to show is level 1P, so dual conformal K, which has this form. So let me just, you could compute lines. Well, not much to say. There's an amplitude here again, there's Q acting outside, and here there is also the action on the form factors. So we have to just expand this object. I won't show you the complete proof, but let me just give you some hints. So for example, let's say you want to check this for HBS operators. So the nice thing about this relation is valid for any state. Let's start with the simplest one, just to get a feeling. Now, if you look at an HBS operator, where there is an immediate simplification, namely, well, this was which we have computed many years ago, but the first line vanishes at the integral level. This is gone. And the second line can also be simplified considerably. It turns out the only piece which survives is the constant piece arising from the dilatation operator there. So you see there will be some difference of terms containing P1, P2, and P3 and P4. Here it is. So this is a very simple integral to compute. So you compute it instantaneously and you get by Dolan written. Now let me give you just some the flavor of the general proof. And this is where the things in common with certain relation that Nicholas mentioned in this talk. Now, after some integration by parts, you find that what you have to worry about is the action of this particular combination of level 1 generators, so Q12 plus Q34 on the scattering amplitude. That's what you want to find. We can just rewrite it as a sum of all the Qij, IS and J, minus this particular combination. Now, the first term from the work of Ramon and Klepka is related to dual conformal K, which annihilates the amplitude. So this term we can forget about. So we need to know about the second term. And the second term, it turns out can be written as a sum of 2 terms. And what you can notice here is that the first piece over here is a level 0 generator, which also annihilates the amplitude. And the second term contains something which is proportional to the dual Coxeter number of PSU 2/4, which is also 0. So this combination of generators also annihilates the amplitude. You can also find in a different way that this combination of generators annihilates the amplitude, namely by using the fact that the Yangian is compatible with amplitudes. And what you find is that after some algebra, is that this, the action on a generic state is proportional precisely to the same combination that we saw before in the specific HBS case. So it's the same integral already, and the result is given by this expression. So I thought the details were good, but it's very simple. I can just give you the highlights. So just some final comments. You can extend this proof to other generators. It's quite actually, you just have to collect the right pieces. And so the first case you can think of is the level 1 generator corresponding to the Q. Now, D is a level 0, you want to find an invariance. So it's interesting to check that you get 0 and you get 0. It's quite and then we just stress again these silent features. So it was very it's very non-obvious to see this relation coming out of this integrated form, which is however very useful if you just want to compute certain matrix elements. And as I said before, this right-hand side really looks like and came out nicely from this amplitude description. Another point I want to say is that in this proof, it was never assumed that integrability, that the theory is integrated. So this is just a completely generic proof of this function, except non-fast across coming out. So let me just conclude and just repeat what just outline what we just said. In the first part, I just discussed some on-shell applications. So on-shell methods apply to the computation of two-point functions. And I discussed two in particular, energy diagrams and generalized entirely. And then in the last part, I just discussed something which we found would be interesting to see in detail, namely how you can connect the action of the Yangian on-scattering amplitudes to the action of the Yangian on the dilation operator, which perhaps substantiates more the idea that there is just an underlying Yangian structure in the theory, which has just very different manifestations which are connected along the steps. And I'll stop here. Thank you very much.
Thank you. Any questions? Comments?
Yep.
So as you know, it's very hard to find the dilatation operator up to 4 loops. So do you think the prospects are, I mean, because you'll have much fewer diagrams.
I think probably the first goal for everyone would be to have a better idea of the two loop. Try to find a complete loop dilation operator. That would be the first one. The problem here is the knowledge of integrals, so that would be something that we think about very hard. But to loops, that's doable. That's why it's time.
Okay. Anything else?
Just want to make a comment. First of all, thanks for the interesting talk. And this thing, what you checked, how the Yang generators act on the dilatation operator. So I think it's a nice consistency check. But there is one way, a little bit indirect, to see that it has to be like that. Because it's just this dilatation generator is a logarithmic derivative of an R matrix. And this R matrix is Yang in like sort of by construction. In fact, this room, Frasek and Tomek Bukowski also a little while ago, we computed 4-leg Yang invariants and found exactly this. Actually, even in the oscillator variables, we found this what we call harmonic R matrix, whose logarithmic derivative gives this dilatation generator in this harmonic, in the oscillator form. And I think actually there's some little thing like to check this precise form of how the Yangian acts on the dilatation generator must come from the fact that it's the logarithmic derivative, and this being a logarithmic derivative, the ordinary derivative would still be because Yangian, but because of this logarithmic.
From the conversation last week, there one assumption is integrability. From this discussion we had last week at Amplitude, so if you want to go in this way, then you have to assume integrability, which is known, so it's not an assumption. And I guess for us, we didn't want to have any assumptions, but perhaps the other thing we wanted to, I should say this proof was very, very recent. What we had in mind was to parallel another proof that we had a number of years ago, and we proved the one dual conformal anomaly, which was conjectured by Drummond and projected in Sokachev. And the kinematics, the structure that the diagrams we have to focus on are exactly the same diagrams which appear here, namely those which are, there is a 4-point amplitude and something else on the other side. So the key thing is the appearance of the 4-point amplitude, because that's what brings along infrared divergences and the appearance of these universality features, namely the 3-level amplitude of the 3-level function. So we had in mind to establish a connection between this feature, these two features. We get a very precise goal and something.
No, it's just all.
That's very good.
Yeah, no, I mean, there's no, I mean, it's just the question how you, what's your logic? I mean, for example, so one can show that the dilatation generator follows, say, from one shot like Matthias Wilhelm showed. And then in another construction, you show that this particular dilatation generator follows from this evaluation of the universal, what's called universal R matrix. And then it has to be like this, but of course it's a very nice consistent teaching. So.
More comments? Questions? If not, let's thank the speaker once more. Our next speaker is Dennis Ken. Okay, so we look into the personal information.
Thank you very much. It's a pleasure to be here. Well, thanks everybody for coming after this nice conference dinner. Thanks to everybody to try to stay awake. So it's my pleasure to talk about this work which is done together with Grishka Kochemsky, Andrei Grozin, and Peter Marquardt on the cusp-anomalous dimension. I define what it is in just a bit more carefully, but the cusp-anomalous dimension is related to Wilson lines. Actually, a Wilson line that has an angle like so. So it will depend on this cusp angle. I'm just mentioning it now because sometimes I know there's a confusion in terms of terminology. Some people think of the cusp-anomalous dimension as the light-like limit of this, but so this is what I think about this configuration, and there's some anomalous dimension associated to this, which depends on the angle. But so that's just as a. And so I talk about calculation of this anomalous dimension in IGST. Well, of course, here at the conference we hear a lot about n=4 supernomials or other supersymmetric theories, and in fact, well, apart from the general interest of wanting to know what this quantity is in IGST, my curiosity was also to see well, known about this quantity in supersymmetric theories, and I was curious, well, how much does it change if we don't have supersymmetry, and can we learn anything from the previous calculations? And so today this is kind of the theme. I'll report on this calculation, but the theme will also be to see how close is it to n=4, and well, as a spoiler, it's actually very close in a very precise way. And so perhaps in the future, integrability techniques for computing things in n=4 can help also with those quantities. So, but okay, let's go back and start more slowly. As I said, Wilson loops were very. Just a reminder, Wilson loops are obviously very important in gauge theories. We need them, or they're important for defining gauge invariant quantities. For instance, if we have a non-local configuration of fields, then we can connect them with a Wilson line, and then this whole object will be gauge independent. Or alternatively, and that's what I'll be considering, we can form closed contours where we identify the endpoints, and then we have another Wilson line or a Wilson loop, and that's also gauge invariant. As I said, we're going to consider very specific contours for Wilson loops. So in particular these two semi-infinite segments which form an angle. So we have this cusp angle, which will be an extension variable. Now, another thing to mention is that there are actually at least two interesting choices for the Wilson loop operator. So there's the standard choice, which was had on the last slide, where you just integrate the gauge field around the arc. However, in supersymmetric theories, it's also interesting to consider a different Wilson loop operator, a so-called an operator which has a property that's locally supersymmetric. And there, the difference is that there's an additional term where we have a coupling to scalar in the scales of the supersymmetric theory. In studies of n equals 4 splitting mills, most of the time people do this operator here. If one does consider the like limit, so the angle becoming complex and going to infinity, then actually the two operators become identical. It's basically this term here is zero. However, since we're going to consider the general angle-dependent case, this will.
But they should they consider each other? No, I for the second term.
Yeah. So I wrote this slide this morning after in the aftermath of the conference dinner. So I will not comment on science.
It's not a unitary operator, and that is important, even if you have lots of time.
This may be metric dependent, so I prefer not to comment. But thanks for making us aware of this. So as I said, today's talk will be about the QCD calculation. So in QCD we don't have scalars, so therefore I consider the first Wilson loop operator. But we can still actually we'll consider a setup where we have a lot of freedom. So I will actually be able to say something about supersymmetric Wilson. So in particular, so perturbatively a lot is known. So in the of the supersymmetric Wilson line operator in n equals 4 supernumerals. So in the planar limit, for instance, 3 and 4 loop, obviously also 1 and 2 results are known. There's the ABC. Also results in the inverse expansion are known, I think at the leading and next to leading order. Then there's as you expand this in the angle, for small angles, so almost going to a straight line, the first term goes as phi squared, and then you have some function which is called Remschraubung function for some reason. This function is known as a function of the coupling and also as a function of color. And then finally, and while in the context of this conference, probably most interestingly, I think this was reported on at previous editions of this conference, two groups independently wrote down the equations for this quantity based on integrability. So is a group of 1 and above, and the other group is Korea, Malacena, and 7. So this is well, how should I put it? It's not known from integrability, but it's that there's TVA equations which integrability, and then in some cases some of these results have been reproduced as well from this approach. So there's this is not exhaustive, but so just to say that there's been a lot of work and a lot of for that operator. So that would be a general motivation, but as I said, now we're going to consider slightly more complicated objects, so the standard Wilson loop operator here. Why is it actually interesting to consider this class monotonous dimension? By definition, it is the UV anomalous dimension of this Wilson loop. So very much like the case when you have local operators, there are short distance singularities. just illustrate this. If you were to do a one, that'd be one diagram to consider, which is this one. And then this is in you have some line parameters, S1 here and T1 here, and you integrate them. So there's a momentum P and Q of the direction, so you have to integrate the calculation. Basically, well, up to some signs, P plus TQ squared. So that's essentially the integral you have to perform. And there's a logarithmic divergence as these two parameters come close to the cusp. So you can see this, for instance, by changing variables. If you put S1 equals rho, some overall scale times Z, and T1 equals rho times 1 minus Z, then this integral would just become, actually the rho integral would become this one, just d rho over rho, times some integral from 0 to 1 over Z. Z P plus 1 minus Z Q squared. And so you see this term here, it has the UV divergence at close to 0. So here I haven't regulated this. Obviously, you do this in a proper way. You have some regulator in place. So this will give the divergence, and then the coefficient here is essentially the one loop Castellani's dimension. So this is just a finite integral which you can carry out, and it will depend between P and Q. So just to get the definition in an elementary way. One thing that's hinted at here already is that, this integral is actually a little bit subtle. There's also a version at infinity. This divergence at infinity is an infrared one. In fact, it turns out that this Castellani's dimension also describes infrared divergences of scattering amplitudes. So that's another motivation for studying it. The primary definition is as a UV divergence of the Wilson loop, but it happens to also describe infrared divergences of scattering amplitudes. Now, there's a number of interesting limits as a function of the angle. So this angle is actually very useful to us. What I mentioned already, when the angle is 0, then we have a flat, we have a straight line, and therefore there are no divergences associated to this object, and therefore the anomalous dimension vanishes. So that's a nice limit. I mentioned earlier that it may be interesting to also consider deviations, small deviations from that limit. Another, but less, little bit more subtle limit, but another geometric limit is the one where the angle becomes close to pi. So that was the straight line, and now the angle, if it is close to pi, then the Wilson loop almost goes back onto itself, and the anti-Wolf potential. In fact, this is true, strictly speaking, only in a conformal theory. You need a conformal transformation to see that. However, even in QCT, we can still use that relation because we know that the terms breaking that relation must be proportional to the beta function. So it will still be interesting to look at that. And then finally, the last limit is a kind of a different nature. These two limits were defined in Euclidean space, but the next one is intrinsically Minkowskian. And so that consists in complexifying the angle and then letting it go to infinity. And what that means is that the segments become null or light-like. And in that limit, there's an additional logarithmic divergence. So if we use this variable x, have a logarithmic divergence as x goes to 0. And the of this divergence is the light-like exponential dimension. That obviously, I don't have to mention, also has a long history of integrability. So here I just use it a lot. I just wrote this variable x, which will appear frequently in the top. So just as a reminder, I said this already. One of my themes of the talk is going to be how many of the nice properties that we know from any exposed videos are going to survive in PCT. I think this customers dimension with the angle dependence is actually quite a good object because it's not too simple. I mean, it has this angle, which, for instance, is going to allow us to learn something about the transcendental properties of the function, the functions appearing in the answer. And we have all these interesting limits. On the other hand, it's not too complicated either. So as opposed to scattering amplitudes, you don't need to carry along all of that list information, for example. So it's not a bad place to study this kind of question. And in order to be able to see a bit more structure, we're going to compute in PCT, but with an arbitrary number of flavors NF. So we're going to be able to play with that parameter. So the plan of the rest of the talk now is this. I'm going to discuss some of the features of the calculations, comparing the N-4 and the PCT answer. And as advertised, there will be some surprises. So the calculation. Sorry, let me just ask for time. Still, good, thank you. So the calculation, well, we start by generating all the Feynman diagrams. This is a rather simple form factor, so that we just use some automated computer programs called QGraph. Diagrams is a representative one. There's a nice feature of having Wilson loops, which is that Wilson loop integrals satisfy so-called iconal. And you can use those identities to advantage. In fact, they allow us to consider only planar diagrams. The way this works is it's actually extremely simple. So there's the identities like this one. That if you have say a two-loop ladder diagram like this one, then there's an identity involving the one-loop square diagram. I think there's so I don't test me on this coefficient, and this is related to a non-planar diagram like so. Where does this identity come from? It's easy to see, for instance, in position space. Remember, we were carrying out these line integrals. So here the line integration parameters are nested. Here they are not, because it's just the overall thing squared. Here they're again nested, but in the other order. So it's just an elementary identity in the theta functions. So that's what it is. Generalizations of this. How are we using them? Well, simply in our calculation, in principle, we need those non-planar diagrams over here. For technical reasons, we don't like them so much. So what we do is we just read this identity the other way around. We want to compute this, but it's simpler to compute those because they're all planar. It's a little bit strange, perhaps, for people who are experts, because usually this is used the other way around. But for technical reasons, we prefer to do it this way. And the upshot of this is that up to the three-loop order, using those identities, we only have to deal with planar integrals. So that's our next job. So we classify all kinds of planar integrals that can occur just by the topology. And next we want to compute them. To do that, we make use of some developments for computing loop integrals. So here are the steps. First step is we have all this set of integrals, and there's a general feature that we can reduce any such calculation to the calculation of a finite set of or master integrals. And there are computer algebra programs which allow you to find these master integrals. So in practice, we plug all these planar integrals into the computer using programs called Fire and a private program by Peter Marquardt called Crusher. And the programs tell us that there are 71 integrals that we need to compute. That's step one. The next step is to, there's a freedom of choosing a basis, and in fact it turns out that the computation becomes a lot simpler if one makes a good basis choice. And here we rely on some inspiration from Kanihama and collaborators in the paper by myself from a few years ago. Basically what you can do is, the idea is you have a loop integral. So there's an integrand, you have to carry out these d-dimensional integrations, and you'd like to know more or less what kind of function you get after integration. It turns out that there's a simple criterion. Instead of carrying out the loop integrations, you look at the so-called leading singularities, which, roughly speaking, consist in replacing propagators by delta functions. Then the integrals become much simpler. You can basically carry them out trivially. And the criterion is you want to define integrals whose leading singularities are just numbers, like 1 and minus 1. That's the criterion, and by conjecture, it's those integrals who lead to who will yield uniform transcendental wave functions. So we use that conjecture, and it turns out that employing such a basis dramatically simplifies our life. And technically, what happens is that we write down differential equations for the 71 integrals. And employing this basis, the differential equations become extremely simple. So we find this very nice set of equations. Let me just explain the main features. So it's a first order system of equations. And so f is this vector of 71 integrals. So therefore, on the right-hand side, we have some matrix acting on the vector. So A, B, and C are some constant matrices. And x, remind you, was the variable here related to the angle. So what you can see very nicely in these equations is the possible singularities of the integrals. And those are actually in one-to-one correspondence to what we were discussing earlier, the interesting limits as a function of the angle of the Wilson loop. So that's very nice. There's some physics encoded there. But practically speaking, it now becomes we want a perturbative expansion in the dimensional regulator epsilon, and this can be done very trivially. It's iterated integrals in these kernels. So we get iterated integrals over dx, over integration kernels dx over x minus 1, and so on. And these are called harmonic polylogarithms, well known in the theoretical physics literature. So in other words, this allows us to compute all these integrals, and now we can put things together. We have the Feynman diagrams. They're related to these master integrals that we plug in the expressions. Well, here's an example. Just a random integral out of these 71. We have some notation for this. This method I mentioned tells us that it's a good idea to double one of the propagators here. There's a specific normalization factor, and then the outcome is that so we compute this, and it's given by this formula here, where it's over 1 plus x corresponds to an index minus 1, and so on. So this is just convenient labeling. But what's important here is that now, as advertised, this formula has uniform weight. And well, here just so you can see this by just counting the weights of each term, you see that the weight of this bracket is 4. Moreover, here's just the first term, but if you were to go to the next term, it would have weight 5, the next term would have weight 6, and so on. So there's a lot of structure here. And obviously, we did some consistency checks, so we checked this numerically, and certain integrals were known previously from n=4 calculations, so we could also cross-check both, so everything works out. So now, as I said, now let's put everything together. Since we're in QCT, that we have to be a little bit careful because there's not just the anomalous dimension associated to the Wilson loop, to the cusp, there's also the intrinsic renormalization of the Lagrangian. So in performing a free loop calculation, we have to reproduce all these renormalization constants, including the beta function and so on. So that's also a very nice consistency checks. In particular, so we do renormalize the Lagrangian. And then we're interested in the renormalization of the Wilson loop, and that's extracted using this formula from the Cantor term. And well, so as I just said, in a theory of a non-zero beta function, the formula for this is a bit more involved, but it's this one here. So you see in particular that at two loops, there's a double pole term which depends on the first coefficient of the beta function, and similarly in three loops there's some terms which depend on the previous loop orders. But that's all fine because we know those terms, and so we have to reproduce them correctly. So these are very good consistency checks. And another comment is that we do the calculation in a covariant gauge. So the intermediate steps in this calculation are gauge dependent, but the cusp anomalous dimension is gauge independent, and so this is another thing that we verify. Now, let me present the results. So before calculation, the 1 and 2 loop results were known. Actually, the 2 loop result is from 1987, so that's a long time ago, involving my collaborator Krzyzewski. This was part of this calculation. So let's look at the first examples. So the one loop function is actually just basically this calculation that we almost finished here on the blackboard. So the interesting piece is this function A1. Now here I have to warn you that it's written in a very strange way. So it's written as this function H1, which is related to this notation, but actually, and it's written with a funny argument, but actually H1 is just a logarithm. So it's logarithm times the rational prefactor. The reason I'm writing it in this complicated way is that this makes it easier to write the results. So it's a nice weight 1 function. The index here also corresponds to the weight. And then at 2 loops, there's two further functions. There's a function A3, which has weight 3, and a function A2, which has weight 2. Again, here one can simplify those functions quite a bit. They're basically logarithms and dilogarithms and trilogarithms. So again, in order to represent 3 loops, I keep this notation. Now, a first comment I can make is that the NF dependence here, so what's really specific about QCT, it only appears in this term here, and it's proportional to the function at the previous loop order. That's a first nice sign. The other observation one can make here is that this function A3 actually is very familiar to people who work in N+4 trinomials. It's actually the same function that appears in this calculation over here. So there's already quite a number of elements which are familiar. But before going further in the discussion, let me present the 3 loop result. So now in 3 loops, first we can decompose our calculation into different color factors, which are here are represented in diagrams. So there's basically the pure gluon piece, then there's some NF squared terms which are really simple, which actually have been known for a while. Then there's 2 terms which are proportional to NF, which have different color structures, CF squared and CFCA. Here the CFCA terms are actually the more complicated ones. Be that as it may, we just compute them. So here the result is given in terms of these 4 coefficients. The most complicated is the pure glue contribution. So here we see that now we have functions with different transcendental weights. So again, the indices correspond to the weights. I'll show you the function on the next slide. What's more interesting is that these other coefficients just as a two loops, these depend only on functions which appeared at the previous loop orders. So this might give you some idea that perhaps something interesting is going on. So we look at that momentarily. Just for completeness, well, this is the full result. It's not particularly pretty, perhaps, but actually, if you're used to looking at results in QCD, then you might actually think that this couldn't be much neater. So it depends a little bit on the point of view. In any case, it's what it is. It's on one slide.
One thing,
Yes?
what comes with a single power of pi?
You want single?
I didn't see any.
Yeah, let's see. So this actually related to this strange way of writing the function that I have here that I kind of glossed over. So we choose this argument over functions, and well, this it doesn't eliminate all terms of pi, but it does discourage these terms from appearing. Perhaps one way of saying where you would get terms which just constants. So constants are sometimes needed to make the property that we were discussing earlier manifest that you want this to be 0 plus phi squared. So this corresponds to x going to 1. So sometimes when x goes to 1, then you get some pi's. When choosing this argument 1 over x squared, as x goes to 1, the function argument goes to 0, and then these harmonic logarithms tend to vanish just by themselves. So that's related to that. But other than that, I can't really have a deeper reason. But it does. Also, I should say that using this representation, there are other representations where the formula is a bit longer, and this seems to be very natural. So it's probably related to this. Okay, so this is the full result. Earlier I showed you all these interesting kinematic limits. Now we can use them as checks. So in particular, a very strong check is the taking the light limits, because the light customers dimension had been known for quite a while. And so in taking this limit, what happens is that these functions have to reproduce this just a single logarithm, which is not trivial because actually these individual functions produce higher logarithms. For example, here we have some log cubes and also log fifths. There's some cancellations between these functions. And what's left over has to be this logarithm with a specific, and this coefficient is this one here. And so this we checked. A more subtle limit, as I mentioned earlier, is the quark-antiquark limit, where the angle becomes pi. And here we expect this behavior. And where all of these are, as I said earlier, are terms proportional to the beta function. So we have a handle on this because we have this parameter nf, which in practice you can use nf to set the beta function to 0. So we can make contact quark-antiquark potential in QCD up to terms proportional to the beta functions. That also works out nicely. Now, all right. So this was the result of the calculation. But now we have these funny observations that some of the NF terms are so simple. So we looked a little bit more carefully, and we came up with some interesting property which we don't really understand. But let me just state what we found. So we had this idea of changing the coupling constant. Perhaps people who do AHAM theory will find this familiar. So we decided, well, let's go for not take some coupling constant, but redefine the coupling. And a nice object seemed to be the light customer on this dimension. So we're wondering what happens from the customer's dimension. We go to some new quantity omega, which is expanded in the light customer on this dimension. So it's just a definition for now. You can deduce now what omega is by expanding the left and right hand side of this equation in our face. If you do so, first of all, by construction, the x to 0 limit of omega is very simple. This is by definition. The question is, what happens to it's not just x going to 0, what about x, what about omega for general values of x? So this we can compute by expanding both sides of this equation. And here's omega is just given by this formula here. Now there's something surprising about that formula. Unfortunately, I've written the solution just underneath. What's surprising is that there's no NF dependence in this formula. So remember, gamma cusp, it had this very complicated, it had this complicated dependence. You see NF squared, NF times this term, and NF times that term, most coefficient, theta 3, 55 over 48, 8, and so on. Just going through this definition, we find that omega is independent of NF. Very, very curious. We don't have an explanation. Could it be that this omega is a function that's just independent of the matter content of the theory? So here we show that up to 3 loops is independent of NF. What if it's also independent of the number of scalars? We could consider more general gauge theory where we also add scalars. That's interesting because then it was full siblings. Well, let's just assume it's the case. What happens if this is actually the same quantity in QCD and then it was full siblings? Well, let's conjecture that. If we do conjecture that, we can turn it around. The like astronomers dimension in n equals 4 is known. So then we plugging into the formulas, we could deduce the angle dependent quantity. So just to remind you, there are 2 things in n equals 4 signals. There was all this stuff which was known, but that's for the supersymmetrical loop operator. So now I'm talking about the bosonic loop operator. So that's a different formula that wasn't known yet. So if we go through this argument, and this comes out for the results in n equals 4 signals for the bosonic loop operator. We can make a test. Because more things are known, and a nice test is this Ganzi-Borg limit. Well, n equals 4 is conformal, so now this relationship should hold without any issues with beta terms. We take the angle to pi or delta to 0 limit, so as a pole, and this is supposed to be the Ganzi-Borg potential. And so we can compare these 3 terms, and this agrees previous calculation by Bowser and Steinhaus. So at least to this pre-loop order, it looks like this true. So surprisingly, the same formula gives you the QCD Caspar-Newton dimension and also the n equals 4 Caspar-Newton dimension. As I said, we don't have a fundamental reason for why this is the case, so it's an open question, and therefore it's a little bit difficult or dangerous to speculate, but let's speculate nonetheless. What happens if this is true at the next loop order? Well, at 4 loops, that's actually an interesting new feature. I mean, if you assume there's many things follow, but there's a specific thing that we can look at, which is particularly interesting. There's actually a new color structure that appears for the first time at the 4 loop order, and you just draw a diagram. So you can look at diagrams which look like so at 4 loops, where you have the gluons being emitted, and the kind of light by light spectrum in here, except that these are gluons. And so this is a term which is proportional to an F. And then the color structure of this is a new color structure. It's not reducible to the ones which we had in the previous loop orders. So that's actually a very interesting open question what this contribution is. And however, now if we make this conjecture about the theory independence of omega, and particularly an F independence of omega, then this tells us something about the 4 loop value. And in fact, so on general grounds, we know that such a term exists. So just looking at color structure, with some yet to be determined function g of x. plugging in our assumption of this NF independence of omega tells us that this function g of x has to be proportional to the one loop function, with just a coefficient that's still to be determined. Now we'd like to say something about the coefficient, and we can do so by again going to the core anti-core limit. Because in fact, there's a, well, not that recent, but more advanced calculation which has been done, which computes that coefficient numerically for the core anti-core potential. So if this conjecture is true, then it implies that this function is this numerical coefficient times the one loop function. And now, to wrap everything up, having determined this coefficient through the conjecture, we can go to another kinematic limit. We can take x to 0, the light-like limit, and then it gives us a prediction for the light-like astronomers dimension at that point. Well, this, as I said, this is a quantity that's not known presently, but it's a very interesting quantity. And very nice to find out whether this is true or not. Yeah, looks like I've been speaking too fast. Energized by when I still yesterday. So to summarize, I've shown you this free loop calculation of the IGST custom dimension. As I said earlier, one of the motivations is that this UV customer's dimension is related to infrared divergences. So in particular, what you can do with this, it predicts all planar infrared divergences for scattering amplitudes, or in general massive scattering amplitudes in the gauge theory, QSD or supersymmetric QSD, what would you like? But then looking at the specific formula, we found that there's something interesting in F dependence was extreme, and we found this of defining a quantity omega, which was up to 3 loops in F independence, and that was to make various conjectures that I just presented to you. I think it's interesting to try to prove or disprove these conjectures. But also, just seeing that there is some relationship, I think it motivates the study of this customers dimension and equals 4 superkingdoms. So as I said, an extreme rich amount of results has been derived from the supersymmetric Wilson loop operator, but very little is known for this bosonic Wilson loop operator in an equals 4 superkingdoms. So this will be my homework problem for you. What can integrability teach us for that object? Thank you very much.
Thank you. Questions?
You have this differential equation on step 3.
Yes.
Can you comment where it comes from? It's just relating different master diagrams.
So yes, let me comment a bit more. I was going through this quite quickly. So there's a general statement that for finite intervals, you can always write down systems of first order equations for that. So in the mathematical literature that we call Fuchsian differential equations. Actually, would like to consider differential equations for a single integral but higher order, but you can always rewrite them in terms of a system of equations of this type. And the fact that the system is Fuchsian has to do with the nature of the singularities. Now, what is special here is that this Fuchsian nature, the fact that we don't have single poles here, is manifest in the equations. This is not obvious if you just start from a random system. And this is where this basis choice comes in a very crucial way. So in general, you can prove that it has to be the case that at the end of the day, near each single is, for instance, near x to 0, you just have a single pole. But this is highly, let's say, gauge. It's dependent on the choice of basis. And so what's really important here for this to work is this basis choice motivated by the unit leading singularities.
Position of poles also.
The position of the poles, and yeah, I briefly mentioned. So this is something you might be able to predict because that's related to the physics. So let's just see, x to 0 corresponding to the light limit. So that's something singular. You expect some pole. X going to 1, the straight line case. You don't expect the singularity, but it's a special configuration. And finally, x going to -1 was the anti-Quark limit. So all of those singular points have some physical meaning. There's actually also x going to infinity, but I didn't tell you, but there's an x going to 1 over x symmetry. So again, all of the singular points here have a physical meaning, so that's also a nice feature of the these equations.
Anything else? You have a question.
In n equals to 4, we now know the quantum spectral curve, not only the TDA for the supersymmetric case, so we could extract probably much more data. Is there any similarity at all in the results for the supersymmetric Wilson loop and for the usual with just one element?
Yes, thanks a lot. Yes, I forgot to, let's see. Let's look at the, it's best probably seen when we look at the omega, and then yes, that for bosonic Wilson loop, for standard Wilson loop operator. One loop, it's the same thing. Two loops, the supersymmetric result is just this function A3. Now there's this function A2. So A2, as the index suggests, is a function of weight 2. So it's an additional piece which has lower weight but definite weight. So it's you might think that there's an additional contribution, like something very well defined which gives that function. So I think that's the first interesting question to ask. Now, let's not draw conclusions too quickly. Let's look at 3 loops. Here, it's perhaps a bit surprising. There's this function p5. So it's a 3 loop 5, which also has transcendental weight 5. So, well, it's still possible that it's given by some specific contribution, but it's not the case as one might have imagined that these extra terms have all lower weights. This is something which has the same weight. But in my going to ask what is there some definite physical quantity, I don't know, perhaps a Wilson loop operator, a Wilson loop with operators inserted or something else, some derivative of Wilson loops which gives these contributions. Just a final comment on this, it does happen that this, in a certain sense, this function A2 is the derivative of A3. So that may be suggested. However, I don't know what the generalization of this statement is at the 3 loop.
Okay. One final question?
So when comparing to QCD, so any conformal theory is not QCD with some number of scalars and some number of variants. We also have you have happening in threshold. So presumably what you're saying is true in low loop or parallel body or new lattices contributing to the diagram.
Yes, so I was quickly speaking what I was presenting for you the calculation of the QCD of arbitrary number of flavors. Now obviously from that first of all I cannot go to QCD, I can go to certain supersymmetric models. I guess the statement of omega was so here we're computing infrared divergences which are mainly associated with the gluons. So you might ask the question in some sense, are these infrared divergences independent of the precise matter content? And it is true that to actually compute n equals 4, you have to compute the correct vertices. Actually, so the right side here. So I presented this as a conjecture, but actually in the meantime we did also include